Hello everyone, and welcome to my presentation, Eliminate Condensate Bottlenecks in Reboiler Discharge. But first, a small disclaimer. I'm just providing tips and concepts today. I'm not reviewing or providing any specific advice on an application. If you want to review another application at any time, please contact me. Let's talk about heat transfer process. We're going to convert processed liquids and vaporize them in a reboil, and there is our reboil formula for the demand heat, and we're going to heat that with our supply heat formula UA delta T. What we're trying to do is we have to equalize the supply heat to the demanded heat. Otherwise, if we put too much heat, we over reboil, and too little, we under reboil. Now there's two methods basically that are used for control: outlet condensate control, which varies the area and adjusts the duty, or inlet steam control, which is going to vary the steam pressure and therefore adjust the temperature. Mr. Henry Kister has just spoken a lot to compare these, so I'm going to focus more now on inlet steam control. And typically we'll see a heat exchanger or reboiler with a trap on the outlet side, and the dynamics look something like shown in the animation. Let's take a look more closely. Here's a kettle reboiler. What a sophisticated piece of equipment with so many precise welds and bends. We're going to put steam in through the inlet control valve. There's our steam trap, and there's our condensate header where we're going to discharge the condensate. I think this is a rather typical diagram, and yet, don't we see some problems with this? We're going to chart the pressures throughout this presentation: P1 before the control valve, P2 after the control valve, P3 considering the pressure drop through the reboiler, and P4 on the outlet. Now, P4 pressure is different from the condensate header pressure. The condensate header will be carrying a certain pressure, but P4 also has to adjust for lift and frictional loss. So some people consider that the total dynamic head, or TDH. Let's take a look at reboiler trouble areas. We can have hammering, channel head gasket leaks, and right now everyone's probably shaking their head, control valve cycling, reduced production, and either condensate waste to degrade or an open bypass. Open bypasses can bleed steam and create a lot of recovery issues: hammer in a return header, elevated back pressures, condensate line blowouts. Probably shaking your head again, right? Okay. So why does this happen? Well, to understand, we're going to take a look at several concepts. The first one is flashing versus filled condensate headers. And I want to talk about a phenomenon known as collapse hammer. So this is in TLV's lab in Japan, and we've taken acrylic piping, pressure around 7 to 8 psi. We've filled it with condensate. We're going to inject pockets of steam. Watch how quickly those pockets of steam collapse. And when they do, you know, the rush of condensate to fill the void creates a lot of hydraulic shock that diverts to the wall. Here we go. Isn't that just phenomenal how quickly that dissipates? If you want to see this or any of our other webinars, you can go to that link and register, and you have no charge access to all of our webinars. The next phenomenon I want to talk about is residence time, particularly in vertical thermosiphon reboilers, and I'm going to start off with a case history. This is one of the most challenging applications to discharge a cold feed into a hot flashing condensate return. So here we go. This is 1.8 bar return header at 130 C. It's flashing condensate. We've got 3.7 bar P1, 2.2 bar in the reboiler, and that's a 2.2 to 1.8 is a 0.4 bar pressure differential. More than enough pressure to get the condensate to discharge into that return header. So why is this a case history? Well, the high residence time, because this reboiler was tremendously oversurfaced, caused the temperature to drop from 136 C to 94 C. And on the outlet about 92 C. So now we have non-flashing colder condensate at 92 C discharging into the top where the flash steam is of a hot flashing condensate line. What do you think is going to happen? Watch. Yes, they had so much hammer that for over 10 years they had to discharge the condensate to grade. What a shame, right? People think steam lines are complex. Actually, they're relatively simple. I think they are. I think condensate lines are really complex. So take a look at this line. The first thing we're going to see is we have hot flashing condensate and biphase flow. Where the ellipse is, you'll see that you can get pockets of collapse like that one just did. To the right of it, on the vertical riser, you see it's a different type of flow. It's got bubbly, frothy foam. When you bring equipment feed into it, the condensate coming out of equipment is typically hot flashing condensate, which by volume is around 90 to 95% steam. And then you come into that with a cold condensate feed into the top of flash steam, and that's going to create some collapse hammer, particularly if you come from a level pot, which, you know, a level pot should have a valve that modulates, but if it sends in a cycle can be 50 gallons from a cycle out of a level pot. That's a lot of condensate into the top of flash steam, creating collapse hammer. In this application here, it would be better if we could relocate that cold condensate to the top of the line and get gravity drainage, but most likely that's not possible. So there was a refinery in the Gulf Coast of the United States, and I went to review. They had 6 condensate line blowouts, some of them in the second and third racks. It was really difficult to access it, so I came up with a solution for them. And what we did is we tried it out in our lab first. So what I want you to see is this is 3-inch acrylic piping, and we're only using compressed air to demonstrate this example. So that means that we're not going to get any collapse hammer. We're just going to see hammer from slugs. But imagine, if you want to see the whole story, you can see it there. And what I want to do is I want to show how, in order to get that bubbly flow up the vertical riser, you actually have to close off the top of the elbow, and then you actually mix in the vapor with the condensate, and you get that frothy foam going upwards. But just imagine if we had a long line of flash steam, in addition to the slugs that you'll see, if you had collapse hammer, and how violent that would be. So watch just for the slugs, and then that's a slug hammer, but then consider that you could also have collapse hammer. Here we go. Watch for the slugs. Here comes the first one, right about now. Second one, there you go. All right, third one. It's pretty dynamic, right? Pretty violent what goes on in those lines. So imagine if you try to add to that by putting in, you got a hot flashing line and you put in a cold feed and you get some collapse hammer going on there at the same time. It can create quite a problem with a top entry. So I came up with a concept instead of the top entry, and that is a side entry concept. And typically a condensate header will be larger than your feed lines coming in. And when that's the case, what you might want to consider is a side entry concept of multiple points. You could do 2, 3, 4 entry points. You could put them 5 or 10 feet apart. You can reduce the bore. You can throttle them so you can balance it. And what you're trying to do is more smoothly integrate the cold condensate into the liquid line at a slower rate so that you don't affect the steam. Of course, if it's, you know, a large feed line, then you could have a steam balance issue anyway, and you're going to collapse it. But if you can just integrate it with the liquid condensate more smoothly, you might have an option to avoid collapse hammer. Of course, this is a concept, and I have not reviewed your specific application. Before you would ever consider to install this, you would need to have a knowledgeable engineer review the application, the specific application locally, HAZOP it to make sure it's safe, because you would never want to do this as a concept without checking it out for your specific application. In the bottom right, I show that you could only do this with a pumped line only. You cannot do this with any chance of getting steam into it, which means you cannot use it with an outlet control valve steam, because those can blow through steam. And if you blow steam into this header, that would be really bad. You could get quite severe collapse hammer from steam coming in at those points. That would be bad. So it can only be with a pumped only system. And there's the side entry concept. But suppose that your condensate header is, you know, 3 levels up in the rack, and you don't want to be able to put multiple entry points up in there. It'd be a challenge. You could have a bottom entry concept where you have a drop leg down and you connect it to a single drop leg, and you allow the cold feed to smoothly enter and integrate with the liquid level from the bottom up. But this is even more severe of a challenge that there's no chance of steam into, because you would blow that pipe apart with collapse hammer. That'd be very dangerous. So you can't use it with outlet control valve, only with pump line. There's some things at the bottom right. Again, this is a concept. You would have to have it reviewed thoroughly by a knowledgeable engineer and HAZOP to make sure it would be safe for your application. But I hope that helps you in some cases. All right, the next phenomenon I want to discuss is stall. I'm uniquely qualified about that because in the late 70s and early 80s, I identified the phenomena and gave it the term of stall by identifying the stall point. We're going to analyze stall and talk about how to mitigate it. But first, I wanted to show you my 21-year-old Camaro. So, you know, any car is relatively sophisticated, even a 21-year-old car. But if you prevent the fluids from evacuating out of the engine, such as by putting a potato or stuffing a rag in the exhaust, the car will stall because the fluids have to be able to be evacuated. The same way, we wouldn't want to do that to the car, and we certainly don't want to do that to a heat exchanger. But this heat exchanger has condensate fluid that has not evacuated from the shell. So what's happening is when steam comes in, it's causing collapse hammer, and that's why I showed you how quickly collapse hammer occurs. Now you see the insert, what's happening from the shock waves that's being formed, and there's the actual tube set. So if you've got tubes that look like that, you probably had stall and collapse hammer. When we walk in sight, it's relatively easy to identify. We'll see telltale signs like a leak color. That tells us for sure that we're going to see stratification like this, 192 to 110 and 82 degrees stratification. This makes it really difficult to control for the operations team. So it's not uncommon that they open the bypass. That can blow steam into the return header. You see water hammer in the header. It can blow steam out of the reboiler. You get a duty loss and you get increased back pressure in the header, which now not only affects that particular piece of equipment, but increased back pressure in the header will adversely affect, to some degree, every single piece of equipment, every coil, every heat exchanger that's using inlet steam control feeding into that header. We really want to avoid that. So why do people show like steam traps? I mean, it could be trap manufacturers. We typically show, you know, heat exchanger very simpler like this with, you know, steam trap going to an atmospheric return. Sometimes design engineers do that. That's the basics, right? You start off and say, well, this is a simple way by putting a trap into the return that's atmospheric, and then your inlet is always greater than your outlet. So you have a positive pressure differential, super simple. You just have steam inside the exchanger or the reboiler. You're just going to vary the temperature of the steam by adjusting the pressure. Everything is great. Yeah, but that's not the real world for refineries and chemical plants. Come on, we're elevating the condensate 20, 30, 40 feet overhead into a return header that's got, you know, 25 pounds, 30 pounds of back pressure. So you can't say you always have positive pressure differential when you have inlet steam control. A lot of times it's negative pressure differential, and that's going to cause a condensate accumulation because there's not sufficient pressure to push it through the trap. When that happens, when you flood the reboiler, you're changing the U value in the flooded section. Only the condensing section has a decent U value. You're adjusting the area, and the whole duty of the exchanger is changing. It's difficult as anything to control that, and people will go and bypass around the trap. So the trap really isn't being used. Let's take a look at stall condition 1 to understand stall a little more closely. And at the top left graphic, watch for the back pressure line in blue. And the wavy line in the top left is the steam curve. So here on high load operation, our pressure point 1 is much higher than the back pressure. That's a positive differential across the trap. We can discharge that no problem through the trap. If we're always going to be above the back pressure line, we only ever need a trap. We don't ever need a pump. We just need a trap. In stall condition 2, we still just need a trap. We've decreased the load, and the pressure has dropped to 0.2, but it's still positive pressure differential. As long as we're above the back pressure, we just need a trap, even if it's throttled, because we're going to have positive pressure differential to push the condensate through the trap. So as long as you just have those two conditions, you really don't have stall. But if our demand reduces so much that in order to equalize to the lower demand, our steam pressure is lower than the back pressure, now we have a problem. We're going to accumulate condensate because we have a negative differential pressure. That's a stall condition. And look how the condensate is accumulated inside of that reboiler. That condensate's not going anywhere because the pressure is not sufficient to push it overhead. That will send a control signal that'll start the valve to open. And here we see the valve is going to start to open. And now it's risen up the pressure to it's equal to the back pressure. While it's ramping up that pressure, still no condensate is moving out of that reboiler because the pressure doesn't have any positive pressure differential through that trap. But we're injecting steam all that time into the reboiler, and that's how you get collapse hammer that creates the thermal stress and the hydraulic shock that you see, which causes channel head leaks or channel head gasket leaks and damages tube bundles. So only when we get above that point will the condensate start draining. When those pockets collapse, it creates a lot of shock, and that's also the uneven temperature. By pushing that condensate level up and down, that causes thermal stress on the channel head gasket area. And of course, the steam contacting with cold condensate causes collapse hammer. In 2004, I wanted to discuss stall further, so I wrote another article. This one was to introduce my extended stall chart. And the article is heat exchangers are underworked and oversurfaced. The key word there is oversurface. You can't put a heat exchanger in for the same amount of surface as the demand. You have to oversurface it to make up for fouling. So this is the extended stall chart I created. There is your demand load and your demand quadrant at the bottom. And here we're going from 100% of load to 0. We're going to supply heat through the upper right quadrant. And our heat will come in the form of steam at this pressure or this corresponding temperature. But we have to oversurface the equipment to make up for fouling. And here we're seeing 55% of oversurfacing by the yellow arrow. Let's have some fun with the stall chart, analyzing the effects of fouling and back pressure. So there's our demand load. And I'm going to insert a back pressure of 10 psig, which you can see on the right-hand scale. We had 55% of oversurfacing. I'm saying the P2 and 3 pressure, P3 pressure is the same, which means no pressure drop through the exchanger. And there's our pressure profile. Now, the first thing we want to notice with our steam pressure profiles, we got a lot of area in that heat exchanger when it's new. So our steam pressure can actually drop down to 20 psig if you read off the right-hand scale where that red circle is. Read to the right of the red circle. Our steam pressure is 20 psig at 100% of load. Following the burgundy line down further to the stall point, our steam pressure drops to the back pressure of 10 at 85% of load. So that means if we're operating above 85% of load, we shouldn't ever hit a stall point. But if we operate below 85% of load, we're going to hit a stall point. So we either deal with the stall or we accept that we're going to have some problems within the reboiler. But as the equipment gets fouled, as the tube bundle gets fouled, it has the same effect as changing the area. So we're going to move the area from 55% of oversurfacing to no oversurfacing. Now we're at 100% of supply area. That is going to cause the pressure to jump up to make up for the change of area. And now we're going to have a new pressure profile line, the burgundy line that we show to the right. Watch how the dynamics have changed as a result of being fouled. Our back pressure is intersected at 55% of load. So our stall point is now 55% of load, not 85% of load. So you see, as equipment gets fouled, you have less of a chance of stall. But this is really where the problem occurs. Over time, people allow their back pressure to elevate. Here I'm showing just from 10 psi to 20 psig. That moves the stall point up from 55 to 65%. And you're like, no problem. I'm working 90% of load all the time, so I don't really have a problem. And you won't have a problem. For 6 months, 12 months, 15 months, whatever, you won't have a problem at all until you clean or retube that reboiler tube set. And that pushes you back to the original 55% of oversurfacing. Now look at your pressure profile. It's the original one. But what has changed is your back pressure elevated, and now you have a stall point, the intersection with back pressure at 100% of load. So it's not uncommon that people say, hey, I just fixed my reboiler, I cleaned it, and next thing you know, your trap's not working. It's not that the trap doesn't work, it's you didn't realize over the last interval of time that you allowed your back pressure to elevate. This is why it's so critical not to let your system back pressure elevate, because it affects the stall point of inlet steam control valve equipment. Now this application needs a pump, so should you use electric or a PowerTrap pump? Well, let's take a look at electric pumps, and we're going to take a look at NPSH-A, the available versus the required. If you have a high reboiler, it's possible you could use electric pumps, but if not, there could be electric pump cavitation. But even if you do use electric pumps, they have a cooling cycle, so on condensate pumps, so discharge is rather high rate, and that could create some collapse hammer. We're going to contrast that with a secondary pressure drainer. But first, I thought it would be fun to take a look at condensate pump cavitation. If you look at the left-hand side piping, we're going to put condensate in through the eye of the impeller. When that condensate hits the eye of the impeller, that is spinning at 1750 or 3500 RPM, and the high dynamic creates a pressure drop in the static condition. So what happens in the impeller is the high dynamic spinning creates a static pressure drop by Bernoulli. Some of the condensate flashes. When it flashes, it erodes the impeller. And because of the condensate and metal around it, it almost quickly condenses again. And that collapse, if you will, that collapse hammer causes other erosion onto the impeller. And that's how you get cavitation on an impeller. The graphics are nice, but there's nothing like a picture. If you haven't seen it, this is what a cavitated impeller looks like. Two different impellers. So one method to handle stall is a secondary pressure drainer, such as the graphic shown. This is our PowerTrap design. So let's take a look at what that looks like in terms of an application. Here's our reboiler, and there's the trap set. Now, there may be insufficient pressure differential to push it 30 feet overhead into a 25 psi G header. But there's probably enough pressure to lift it up 2 or 3 feet into an open receiver and then pump it out with a pump only. The only thing we have to deal with here is the flash that's coming off the top of that receiver. And it may be very minimal. But I want to show you another thing called a pump trap combination, where everything is in one body. This was my original design and patented with another gentleman in Japan. To understand the operation for the pump trap, take a look at the dashed line on the left. This is the condensate level. As long as the condensate level stays below that line, that means that we have a positive pressure differential, and that'll push the condensate through the trap mechanism. And that's all we need is the trap mechanism. But if the condensate elevates above that line, it means that you can't discharge the condensate. So it's building up inside the body. That indicates a negative pressure differential. It has to be pumped out. We're going to pump it out by bringing in a secondary pressure. Look at the valve train to the right. There is the motive valve that's going to bring in the steam pressure to pump it out. And we want to close that cavity off at that point so we can pressurize the body. So we're going to close off the exhaust valve, which is normally open for venting. And that's the operation. So please take a look at the animation. We're going to see 3 condensate level cycles as a trap. So there's the first one, discharging through the trap mechanism at the bottom. See the valve mechanism moving up and down. That indicates positive pressure differential to push it through the trap mechanism. No pumping is needed. If you notice, the motive valve is closed. Now the condensate elevates up. It indicates a negative differential. We're bringing steam in to push the condensate out. And there's a cycle. Let's see it again. So we're venting out now. The exhaust valve is open. Now we're going to pressurize the body with motive steam and discharge it out. Each cycle is about 8 gallons, and that's relatively consistent among manufacturers for 3x2 units. They go into a package unit that looks like this. The receiver that you see is actually not a receiver, it's a reservoir, it's closed. When they're open, we call them receivers. When it's closed, we call them reservoirs. This would be similar to a level pot. So there is a typical package system. We like to see the elevation at the bottom of the tank 60 inches high, because that gives you the least amount of pump traps necessary. If it's lower distance than 60 inches, you may require an extra pump trap. So it's better to keep it 60 inches if you can. This is the perspective alongside someone that's around 6 feet tall. This is how it hooks up to a reboiler. So there's the connection to the package pump trap system. And I just show the condensate is going to flow in here for around 13,000 pounds an hour for a single system. And the balance line is here. Now in a horizontal reboiler, it's critical that it connects to the channel head outlet right here. As shown, it can't connect anywhere else and get a proper operation. It will not work well unless it connects there. And of course, reboilers have a lot more capacity than that in a lot of cases, so you just add extra units. I want to talk about SPD redundancy though, when we're talking about adding extra units. We have to anticipate a service need, because everything mechanical is going to require service at some point. So why not install an extra unit? I mean, when you think about how critical reboiling is, just install an extra unit. Here's what I mean. Instead of saying this is a twin pump trap set for 26,000 pounds an hour, no, consider it a single with a spare. And is this a triple? No, it's a twin with a spare. And is this a quad for 52,000 pounds an hour? No, it's a triple with an installed spare. These are functional spares, so operators can go and check them on a regular basis. It's unlikely that more than one would require service at any time. So you keep the reboiler in operation, everything is working well while they repair the one unit. In order to be able to test them, there's two important valving additions. One is a test and drain valve that fits off the back. This is a small valve. I prefer it over gauge glasses. It has to be manually operated while it's in operation, but it's easy to use. And if you're in a freezing climate, which most of the United States is in a freezing climate, but this webinar will go all over the world. But if you're in a freezing climate, install the pre-freeze valve. Well, that completes this first presentation, Eliminate Condensate Bottlenecks in Reboiler Discharge. I hope you watch the next presentation on designing systems to drain reboilers. But right now I'm open for questions, and you could ask questions right now or contact me at any time. Thank you for attending my presentation, and I'm open for questions. Thank you.